Now I need to delve into one of the large conceptual issues for dinosaurs that it kind of goes up and down over the years, whether we think this is solved or not solved. The whole question of whether dinosaurs had warm blood or cold blood. And we'll talk more about that in just a bit, and I'll give you a better sort of way to segregate this out. So modern reptiles like lizards, turtles, snakes, their bodies are at the mercy of the ambient temperature, meaning as the temperature heats up outside, they heat up. If it cools down, they cool down. Whereas mammals like you and I, we are not. We regulate our body temperatures. We thermoregulate. So dinosaurs are reptiles, but of course here's a cute little cartoon. I'll let you look at that yourself later. But let's look at this. There's a whole bunch of evidence that summarizes the support or the falsification of whether or not dinosaurs were warm-blooded. And right off the bat, I want to get you to forget about the whole terms warm-blooded and cold-blooded. Instead, you need to think about ectothermy, where the body heat is from an external source, basically laying out in the sun and heating up, or endothermy, where body heat is generated internally. And you can see there where I laid out the modern organisms and how they would be classified as either warm or cold, and then ecto or endothermic. The graph itself is an interesting one. It shows the ambient temperature, that's the temperature outside, degrees Celsius. You might not be super familiar with that, but it's cold here, freezing to higher temperatures, and then body temperatures. And as you would expect, cats, rabbits, kangaroos, platypus, these are the mammals. Notice it's a straight line across. If it's cold outside, the cat has a certain body temperature. If it's hot outside, it also has a relatively the same body temperature. Compare that to alligator, gopher snake, salamander, so two reptiles and an amphibian. If it's cold outside, they're cold, and if they have this strong positive slope, that means as their environment heats up, they heat up. So there's the segregation between the two groups. And then the big question is, were dinosaurs ectothermic or endothermic? We have a whole bunch of ways of looking at this, and some of them are straightforward thinking, and others involve a bit of twist of logic. So let's think about this here. Living endotherms mostly have what's called an upright gait. So endotherm would be a warm-blooded creature, and they have a gait or a stance like this here, whereas ectotherms tend to have a sprawled gait, like a lizard, this one over here. For dinosaurs, most of them actually have an upright gait. But some of them have some sprawling, and some sprawl in the front and upright in the back, and so you can't just universally say that if you have an upright gait, you are an endotherm, or a sprawled gait, you're an ectotherm. And dinosaurs then don't answer that question because they can have both. If you look at the activity level and agility of different organisms, today generally most ectotherms are slow and sluggish, but endotherms, again, think about your cat or a mouse or anything like that. They have high activity levels. They're very agile. Some dinosaurs fit the slow and sluggish model, but a lot of them, especially theropods like this raptor here in the image, have body frames and skeletal masses that suggest very high levels of speed, agility, and activity. So you're starting to see the whole idea that some might be, some might not be, as far as the question of endothermy is concerned. Relative brain size. In general, endotherms require much larger brains to process and control those extra systems, and so mammals have these larger brains. Dinosaurs, we have what's called the lizard line. Lizards defined as 1, so relative brain size to body size. And if we think about it, above this would be, well above this would be mammals, and below it the reptiles and other amphibians. And if we look and compare brain size to body size for different dinosaurs, notice the giants, sauropods, as well as then ankylosaurs, stegosaurs, ceratopsians. They're all below the lizard line, which would argue that they are ectothermic. But then if you look at ornithopods for the ornithischia, and then some of the select saurischians, they are well above the lizard line here. So maybe, again, evidence of some being possibly ectothermic, some endothermic. Endothermic brains require much greater complexity, larger cerebral portions. Dinosaurs simply don't have that. And so brain casts, remember that's sort of a fossilization of the inside of the skull, with the space that the brain would fit, would suggest that dinosaurs are ectothermic organisms. Feeding adaptations. Living endotherms, like a large one especially, like an elephant, eat lots and lots of food. They have to constantly eat to maintain this high metabolism. And so evolutionarily, we see lots of different adaptations of their teeth, their jaws, their skulls. And as it says here, like an elephant is a natural-born living food processor, we do have some, like this hadrosaur, which is an ornithopod, that also have this sort of food processor effect. So perhaps. Here's a strong bit of evidence here. If you slice through bone and then put it under a microscope and examine it, ectotherm bone has very few channels, and it has growth rings. So these little holes, so the top picture is ectotherm bone, and the holes are few and far between, and you see these growth lines. Notice there's sort of concentric lines around this. Endotherm bone, on contrast, has many holes through it. So you see both large and smaller holes here. But some of these dinosaur bones also will have the growth rings like living ectotherms. So bone histology had great promise for sort of segregating and finally answering the question, but the jury's still out for a lot of these. Blood pressure. Being an endotherm in today's world requires a high blood pressure with rapid blood circulation, and living ectotherms are much lower. So these are living organisms here, and look, mammals and birds, these are the endotherms. They have high blood pressures. That's what's being measured on the y-axis. The living ectotherms, reptiles and amphibians, have significantly lower blood pressures. Well, we can't really measure dinosaur blood pressure because we don't have their blood, but we use something as the measure, literally taking a tape measure and measuring the distance between the heart and the brain. And living endotherms have long H to B distances. The distance from the heart to the brain is very long compared to ectotherms. And dinosaurs have this as well. And notice that some more so than others. So theropods and sauropods generally have the longer heart-brain vertical distance. So perhaps some. Dinosaur hearts. We don't have any preserved hearts. But think about this. We have endotherms. Mammals and birds have a very complex four-chambered heart. Ectotherms have only two. And crocodiles are right in the middle. They are intermediate. Crocodiles and birds are taken as the groups that are most closely related to dinosaurs or the fossil dinosaurs. We're going to learn later that birds are dinosaurs from our modern perspective view. And so birds, mammals, have four-chambered hearts. Crocodiles, the group most closely related, has an imperfect four-chambered heart. So perhaps it's another bit of evidence that dinosaurs are on their way towards true endothermy. Looking at just occurrence data, where are they found? Endotherms are distributed pole to pole. You can go North Pole to South Pole. like these birds and mammal bar graph here, and we can find living endotherms. Ectotherms, well, you see the various constraints there. Turtles, crocodiles, snakes, lizards, they have to have warmer places in order to survive. Dinosaurs, they have a wide, much wider paleolatitudinal range. And we'll talk about that in one of the upcoming lectures, looking at dinosaurs that we know lived above the Antarctic and the Arctic circles. So it's very, very possible that dinosaurs had some way of regulating body temperature to live at these extremely high latitudes. Predator-prey ratios, so ecology. Endotherms have much lower predator-to-prey ratios. Endotherm predators require a heck of a lot more food than ectotherm predators, and so there are far less of them. So there are like if you think about the lions on the plains of Africa, there are far less of them as a percentage of total biomass in communities compared to lizards or insects or things like that. Dinosaur faunas, very, very similar. We don't have a lot of good whole ecosystem collections of dinosaur fossils, but where we do, the whole idea is that the predator-prey ratios are very, very similar. And then turbinates. Turbinates are these, it's a set of bones, a weird set of bones that are present in our noses, in our sinus cavities of endotherms. And so here's a cross-section through a head of a dead person here. So it's both flesh and bone. And so you can see the eye orbits. Here's the nasal passages. And these highly curved, convoluted black things here are the cross sections through these turbinate bones. They are adaptations for quick breathing, high rate of oxygen consumption. There's oxygen transfer across them. Dinosaurs don't have them, although some people have said that perhaps there are some that do. Okay. What do you say? When all of this is said and done, the question is not fully answered. We just don't know that dinosaurs have evolved or developed endothermy, true endothermy, but the evidence might suggest that some perhaps did. And if you look at this, I could say right away that most of these ornithischians, Fabrosaurids, which we didn't really talk about, but ankylosaurs, stegosaurs, ceratopsians, pachycephalosaurs, there's no good evidence to suggest that they had a warm-blooded or endothermic conditions. Ornithopods, including the hadrosaurs, the duck-billed dinosaurs, some tantalizing evidence that perhaps they did. And then if we go to the Saurischia, there's some evidence for sauropods. There certainly is, if I put this extra little branch here, this would be, what other sort of high-ranking or highly evolved saurischians there might be. There's evidence over here. So perhaps warm-bloodedness can arise or has arisen at several places on the cladogram, perhaps for the Ornithopoda, perhaps for the sauropods, probably or most likely for the theropods. It's an interesting question.